tricky finding these things, and you can always go to the one that's on engrcs.com as a kind of last resort. But yeah, so Mouser is a better choice than DigiKey for searching for things. DigiKey just gives you like 10 million results, and they're not necessarily what you're looking for. So if I search for PLD, I don't know what any of these things are. Let's just search for that and see. So there's CPLD, complex programmable logic devices. That's kind of a little bit of a different thing. So I don't know. Programmable logic. Maybe spelled right. Programmable logic ICs, maybe. It's kind of a hit and miss, and that's part of the point of the exercise, is just kind of like getting some practice at digging these things up. I'm not actually seeing anything on Mouser that's going to be terribly applicable. Another possibility is to just go with Google, like programmable logic device data sheet. And this sounds like a programmable device. So let's see if that has a fuse map. So that's got a fuse map. So that's some kind of programmable device. But it's a surprisingly hard thing to find, right? So you can go with the one on engrcs.com under the component specifications. That's similar to this one, and they're all kind of more or less the same at some high level. But I just kind of wanted you to try a few different sites and sort of see what's available and get some ideas from there. And if you go to the NGRCS site and find a specific one, you should be able to take that part number, AT16 whatever, and put that into Mouser and find that chip, and then you can find out things like pricing information and so on.
I went on Mouser and I typed in simple programmable logic devices.
Mm-hmm.
A lot of them came up, and I was able to they basically just have AND gates and OR gates.
Okay.
So it's really easy to implement that.
Did you say simple because it said complex and you wanted something simpler? Oh, that's pretty smart. Okay, so simple programmable logic device. Okay, cool. I might already be down in a search tree. Okay, those look good. All right, cool. So did you find one to use in the end, like from the NGRCS or something?
I think I took one from those. I don't think it's the right one.
Well, there's no right or wrong one, as long as it's got a fuse map and you can do something with it, or I mean, it's a few points in the lab for that part of it anyway. It's more about just sort of looking around. Yeah.
Actually, on the lab, it asked to do a timing diagram.
Mm-hmm.
I wasn't sure what it was asking for. I was assuming it was for the 555 timer, or was it over all the components?
So this was the one where we said you can have a 555 output. That's your clock, so that's just going up and down. It's actually not symmetric, but it's faster to draw symmetric. So that's the clock that's feeding into what? It's feeding into a counter, right? So here's your 7493, and if you wired it the way that I suggested, where you feed into input B, then your outputs from here I think were B, C, D, and you should see something like this. Right, this output toggles every other time that the 555 changes from 0 to 1, and every time that B changes from 0 to 1, the next bit is going to change from 0 to 1. And every time that this changes from 0 to 1, actually from 1 to 0, but anyway, if you actually look at what the circuit's doing, you can draw what the output of your counter is, right? And then this goes into your 8 LEDs. and LED 1 turns on for one of these, and then LED 2 turns on, and they do something like this. And then LED 0 repeats. So you want to draw a much neater diagram than I just drew, preferably on graph paper so things are lined up. But basically it shows what the timing is for all the different points in your circuit, right? And it's sort of driven off of the clock, which is coming out of the 555. And at the very least you want to show what the 8 LEDs do, because that's kind of the final output from the system. But it's useful to sort of know what the inputs to that 138 are doing, the output of the counter. And counters are interesting. So let's just look at a 2-bit counter. Right, if we just had a 2-bit counter, it's counting 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, right? If you draw the timing diagram for that a little more carefully, B0 alternates between 0 and 1. And B1 changes whenever B0 drops from a 1 to a 0, right? Here B1 is dropping, that's when B1 toggles. Here B1 is dropping, that's when B0 is dropping, that's when B1 toggles. So B1 actually changes on the falling edge of B0. And if we had a third output bit, our count would look like this. And B2 toggles whenever B1 changes from a 1 to a 0. Here B1 changes from a 1 to a 0, B2 changes. So B2 is only going to respond to B1, and it only looks when B1 drops, and then B2 toggles. B1 drops, B2 toggles. And if you look at this value of your B's, this is 0, 0, 0, this is 0, 0, 1, here this is 0, 1, 0, here is 0, 1, 1, and here's 1, 0, 0, and so on. So that's a pattern you'll see a lot, right? That's the standard pattern for a binary counter. And if you had a fourth bit, B3, right, that would be 0 throughout all of this, and then at this point right here, when B2 drops, B3 would go to a 1. That's putting a 1 right here on the end. And this is sometimes called a ripple counter, right, because this bit is changing in response to this, which is changing in response to the bit before it, and so on. And so when you come all the way to where you've got an output like this, and this least significant bit changes to a 1, that transition from 1 to 0 causes this bit to toggle, and this change from a 1 to a 0 causes this bit to toggle, and that change from a 1 to a 0 causes this bit to toggle, right? And so the effect of that first bit toggling kind of ripples through all the bits. And it's similar to what we saw with the adder, where we had a carry rippling through. And there's a homework question we're going to talk about that deals with counters. That's part of why I'm going through this. All right, so other Lab 5 questions. I signed off on a bunch of experiments, so they look good.
About that homework question, is that, are you talking about AU?
I think so.
I was actually going to ask you about that, but you must have gotten notes.
Yeah. So what do we want here? We want What is the mod of this counter? Is this counter useful? Change only the value being loaded. Okay, so let's talk about the solved question here, which is similar. Okay, is this counter useful? What's the mod of this counter? Change a value to obtain a mod 9 counter. Okay, so let's talk about this mod business. So when we talk about something like a mod 7 counter, has 7 different outputs. Typically it would be 0, 0, 0. It goes in the usual order. But it's only got 7 outputs, which means after it outputs its 7th value, which is 1, 1, 0, it's going to go back to the first value. Right, so that's what mod 7 means. A mod 10 counter would have 10 different output values, basically from 0 up through 9, then it would go back to 0. And it's mod as in the modulus operator, if you know about modulo operators in math or in programming. If not, we'll get to them later. All right, so let's look at this circuit. So this is a binary up counter. Counters can be up counters or down counters. Okay, fairly obvious definition. An up counter counts 0, 1, 2, 3, 4, 5. A down counter counts 5, 4, 3, 2, 1, 0. Okay, and when it gets to 0, if it's a down counter, it goes back to all ones. So if it's a 4-bit down counter, it would count down 3, 2, 1, 0, and then it would go up to 15, 14, 13, 12, and so on. A 4-bit up counter would go 0, 1, 2, all the way up to 14, 15, and then back down to 0. Okay, so this is an up counter, and it has a clear input. And the clear input, CLR, has a little bubble next to it, which means this is active low. Okay, so if you put a 0 into that input, it should clear it. That input is tied to VCC, so it's always putting a 1 in there. So we're not using that clear input. We're not clearing this counter, which is good. If we were putting a 0 into that clear input, the output would always be 0, because it's always being cleared. So the counter has a clear option, but we're not using it. Okay, we've got it basically turned off. It also has a load input, okay? And load basically says, I want to take the values of A, B, C, D over here, these are inputs, and I want to load those into my count. So this thing is minding its own business, counting 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, going through the usual count routine. But at some point, I can put values on A, B, C, D, and I can raise that load line, and all of a sudden, it jumps to whatever value I put on A, B, C, D.
It only looks like it's, look, the only thing loading into a load is QD.
But the only thing loading into A, B, C, D is 2 zeros on C and D, and then whatever QD is on A and B, right? But if we ignore that, if we just think about this as just an isolated chip, right? Does everybody get what these inputs do? Right, if I were to say like 1, 0, 1, 0 and hit load, suddenly my output would be 1, 0, 1, 0. Okay, so it's a way to load an external value into the count, no matter where you are in the count sequence.
So are we not paying attention to how it's wired?
We're going to pay attention to how it's wired, but I just want to go through some of the details of this counter, because there's a lot of details. So there's notes over here. So this says clear quotation mark, right? Remember, a quotation mark is a way of saying clear bar, which is just a way to say this is a clear with a bubble in the front. Okay, so clear bar and load, and it says these are synchronous inputs. So this is the next detail, synchronous versus asynchronous. Okay, synchronous means synchronized with something. What's the something we're going to synchronize with? A clock. Okay, so a synchronous input is an input that pays attention to the clock. Which means that if we say clear, it doesn't immediately clear the counter. It'll clear the counter the next time that the clock ticks. Okay? So we've got this, forget about this circuit right now. We just got the counter, it's got a clock coming in, it's counting 2, 3, 4, 5, 6. We put the clear input to ground, the output is still 6, right? Doesn't do anything until the clock actually ticks. If I put the clear input to ground and then I change my mind and I connect it back to VCC and the clock hasn't ticked yet, nothing happens. Clock ticks, it goes on to 7. Okay, so synchronous input, which is what these are, only get looked at when the clock ticks. Okay, so clear is synchronous. Doesn't matter for this circuit because clear is always tied to 1. But the load input is also synchronous. So we can put values on A, B, C, D, and we can set the load line to 1, but it doesn't do anything until the next clock tick. Okay. And then it tells you clear quote sets all the outputs to 0. Load allows values on A, B, C, D to go into QA, QB, QC, QD. And QD is the most significant bit, QA is the least significant bit. Okay, now we got everything we need to actually look at the circuit. So suppose this thing starts off at 0. Okay, we don't know if it'll start at 0, but let's just suppose it starts at 0. And I'm going to make a table over here. QD, QC, QB, QA. And I'm just going to fill this in. So this is just going to count in the usual way, right? And you noted that the load line is connected to QD, right? And so if QD is 0, that load line is a 0, it's not doing anything. So this is really going to just count normally. Up to 7. Okay, we get to 7, the clock ticks again. This thing is going to count. The load line is still 0, right? Because 7, we've got 1, 1, 1, 0. QD is a 0, so load is 0. The clock ticks. We count from 7 up to 8. This is going to go to this value. Okay, now at this point, 0, 0, 0, 1, QD is a 1, goes all the way around, the load input is a 1. Alright, but it's not going to do anything yet because the clock's already ticked. So it's going to hang out here until the next time the clock ticks. But what's going to happen on the next clock tick? Say again? It's going to load the inputs. Okay, so what are the inputs? What is A equal to?
1.
A is 1. What about B?
1.
And what about C? C is 0 and D is 0. All right, so the next time the clock ticks, it's going to use these values from A, B, C, D. It's going to load that into the counter, which means on the next clock tick, that's going to be what the outputs are. And now, since QD is a 0, that comes around, the load input is a 0 again. So now it's just going to count normally. So the next time, it'll go to 4, and then 5, and then 6, and then 7, and then we're back in the situation we were in before. 7 will get incremented to 8, but now the load line is high. It's getting ready to load into 3. The next time the clock ticks, it goes back to 3, and that pattern just repeats.
Is there a reason we stopped at 1, 0, 0, 0 instead of just continuing on?
Because, yes, because when we got to 1, 0, 0, 0, that 1 on QD is also going back into the load input.
Right.
Right? And the load input, if it's 1, says on the next clock tick, load in A, B, C, D.
Okay.
And so that's why we went back to 0, 0, 1, 1. So if we look at these values as integers, what is this thing doing as it counts? It's really going 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, and so on. So it's a weird kind of counter, right? It starts at 3 and it rolls over after it gets to 8. But that's potentially useful, right? So what is the mod of this counter? Well, I think it's supposed to be considered a mod 6 counter, right? So it's mod 6 because it has 6 unique values, 3, 4, 5, 6, 7, and 8. All right, is this counter useful? Well, it depends on, you know, what kind of circuitry you need to drive your spaceship, but you need something that counts from 3 to 8 and goes back. Yeah, it's useful. So that's good. Okay, change only the value being loaded at the inputs to obtain a mod 9 counter. So this is a tricky part. So you want to change what you're putting into A, B, C, D so that this thing counts through 9 unique values. And it's a bit of a trial and error thing. And we're not allowed to change the fact that this output goes back to load. So every time that we get to 8, this thing is going to reset. If it resets to 3, then we get 3, 4, 5, 6, 7, 8. We get 6 unique values. What value should it reset to so that we get 9 unique values?
0.
Set it back to 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, and then go back to 0. That's going to be a mod 9 counter. So how do we change the circuit so that when it resets back to a 0? Well, just change AB to also be connected to ground. And now every time that QD goes high, which is when you're at 8, the next clock pulse is going to load a 0 in. And now you got a really useful circuit because it counts cleanly from 0 all the way up through 9, then goes back up to 8, and then goes back to 0. So if A, B, C, and D were grounded, the counter would count from 0 to 8. That's mod 9. All right, and then 8U is very similar, right? So it's a different circuit. What is different about this? So A and C are connected to ground, B and D are connected to VCC, logic 1. So your inputs on your preset here are 0, 1, 0, 1. But do the same kind of analysis, basically, and see where you end up. All right, what else? Yeah.
A lot of these require truth table. Is there a specific strategy or specific way not to write truth table without writing too many very large truth table for a lot of stuff?
Is this for the state diagram questions?
The state diagrams and analyzing the logic circuits.
Yeah. Yeah, you're gonna make really wide truth tables, and like I say, we're gonna go through one here, and then you're going to work them on the board, probably after the break. But yeah, we'll talk about exactly what should go in that truth table and what can go in that truth table. All right, let's look at question 9. So this is the one about the fastest clock that you can use for a circuit. So let's do this in a little bit more generality. Remember what our basic state machine looks like. So we've got some sort of memory. And we've got some sort of combinational logic. And this is basically what your state machine looks like. there's some inputs and there's some outputs. But the real core of your state machine is basically a bunch of flip-flops and some random logic. And the output of the flip-flops goes into this logic, the output of the logic goes into the input of the flip-flops. And you have a clock which tells the flip-flops go to your next state based on your inputs. They go to a new state, get new outputs, that changes the combinational logic, it feeds back in, and that's how the system moves from one state to the next. So a good question is, how fast can we run this clock? Right? The faster you tick this, the faster the system goes from one state to the next. And if this is doing something useful like picking winning lottery numbers, you want your clock to go as fast as possible, right? So you can buy a lot of tickets. But there's a limit to how fast you can run your clock. If this combinational logic is really slow, you can't ask this thing to update faster than this logic can take the inputs and produce new outputs. And remember, everything has propagation delay. So this has some delay, which we can just call tau sub p. That's propagation delay. That's the maximum time it takes from changing an input to getting correct outputs. So this is propagation delay. And finding maximum propagation delay is tricky, especially if you have a million gates inside here. How do you figure out what the longest time is that it might take from changing one input to changing all of the outputs? You have to basically trace every possible path from every combination of input changes to every output, and then find the worst case. There's software that does this for us. But, you know, without that, you do this by hand. And you make some good guesses maybe, and then you throw in a little bit of padding, right, just to be safe. So there's a propagation delay associated with that. With memory, remember there's a setup time and there's a hold time. Setup time is how long inputs need to be stable before the clock ticks. Hold time is how long the inputs need to be stable after the clock ticks. All right, so one of the realities is that hold time is usually a few nanoseconds, right, because flip-flops are pretty good devices. Propagation delay over here is usually a lot longer than that. If you've got 5 levels of logic, it's 5 times the propagation delay of one gate. So usually by the time that our inputs have propagated through to the outputs, we're way past the hold time. So usually we can ignore this. Because it's much less than the propagation delay time. All right, so let's say that the clock has just ticked and the flip-flops are producing an output. Okay, we need to wait at least this much time, the propagation delay of this combinational logic, before the output of this logic is correct. And then those outputs are going to come in here to the inputs of the flip-flops. And we know that when we change the input of a flip-flop, we have to leave it at its current value for at least the setup time. So if we take the propagation delay and we add the setup time, that's the minimum amount of time we have to wait between clock ticks. Clock ticks and all of this stuff starts happening. If we clock again before this much time has passed, we might not have a stable setup. So minimum time, so time between clock ticks has to be at least propagation delay plus the setup time. So time between clock ticks and frequency of the clock, they're reciprocals of each other. Okay, so frequency of the clock has to be less than or equal to 1 over the sum of the propagation delay and the setup time. So our maximum frequency that we can run the clock at is just 1 over propagation delay plus the setup time. And that's all that's happening here in our one-line solution for question 9. We have a circuit with a hold time of 5 and a setup time of 10. But this set assumes there's no other limitations. So in this case, there's no propagation delay, right? And so the only thing that we have is, so let's do this. If ignoring propagation delay, then we do need to take into account the hold time, right? We're going to ignore it if we've got a reasonable propagation delay. If we're not looking at that, we have to clock ticks. We have to leave those inputs stable for the setup time, right? And we also have to keep them stable for the hold time. So the time between clock ticks has to be at least this, and the frequency has to be less than 1 over that. Okay, so that's what's being done here in this example. We're ignoring propagation delay. Hold time is 5, setup time is 10. That's a total of 15 seconds. Your clock period, T clock, has to be at least 15, and so your frequency has to be less than 1 over 15 nanoseconds, right, which is 10 to the 9th over 15, so 66 megahertz. So same setup for question 9, except your hold and setup times are given in picoseconds. So 50,000th of a nanosecond, 150,000th of a nanosecond. But same analysis. Again, practical terms, we have software that does this for us, but it's important to know why this is the formula that you use. All right, good to go on the homework. All right, let's take a quick look at Lab 6. So Lab 6 is the final version of your traffic light system. So experiment 1, you're going to build a delay circuit, which we're going to talk about in a moment. And then experiment 2, three-way intersection. And each direction has one lane and has red, green, and yellow lights. And you should only have one green at a time. And anytime you go from green to red, you should go yellow for 2 to 4 seconds first. So it's like a normal traffic light, right? Green, yellow, red. And then when you're ready to go, you can just go from red to green. And your deliverable, sketch of the intersection, all the usual stuff. Sketch of the intersection, system diagram, truth table, K-maps if you simplify, equations, and then the full wiring diagram. It's going to be a big circuit, probably 2 protoboards, okay? But it's going to be a very straightforward circuit if we do a trick, and we're going to talk about the trick. And then make a test plan, demonstrate it, get a sign off on it, put it all together. Hints. Always pay attention to the hints in these labs. There are multiple design options. One option is to use the logic from the three-way intersection designed in an earlier lab and use the output from that design as an input to delay circuit that is described by the following timing diagram. And then here's a possibly useful timing diagram for how our light should behave. Our light should be green. When the green light drops, our yellow light should go on for a few seconds. When the yellow light drops, the red light should go on. Okay, so let's talk about experiment 1 first, because that's going to be a big piece of experiment 2. So experiment 1 is a delay circuit. And it should be a 2-second delay. What does this do? Let's look at a system diagram. We've got an input you got an output. Okay, in a timing diagram, here's what it does. If you raise your input from a 0 to 1, about 2 seconds later, your output raises in response. When you drop the input from 1 to 0, about 2 seconds later, your output drops. If you take your input and you just do a little blip, raise it up and drop it down, about 2 seconds later, your output should repeat that little blip. So it's like a slow motion machine almost, right? Or a time machine of some sort. It takes whatever happens to the input and it presents it to the output, but like 2 seconds in the future. Okay, it's a really cool circuit once you get it built, because you can put a switch on the input, you can put an LED on the output, and then you can like flip the switch really quickly and step away, and 2 seconds later the output goes blink blink. Or you can turn it on and leave it on, and 2 seconds later the output comes on. All right, so you get what it's supposed to do, right? Okay, it's really easy to know if it's doing the right thing or not, because it just kind of looks really cool once it's working. So how do we do this? We're going to use the 555, okay, wired for about a 2-second pulse, and you're going to use a new chip, the 74LS374. This is a flip-flop. Flip-flops rock, so this will be good. And it's actually an octal flip-flop. It's got 8 flip-flops inside. So let's look at the data sheet. .374, yep, okay. So the picture on the top is the 373, that's not the one we're using. We're using the 374 down here on the bottom. It's got 8 flip-flops inside. Ground on pin 10, power on pin 20, no surprises there. So each of these is a D flip-flop. Has a D input, has a Q output, and has a clock. All the clocks are tied together and are connected to pin 11. And this is tricky. There's a little inverter here on pin 11, and then these clocks have little bubbles on the front of them, which means that the clock gets inverted and then it gets inverted again, so it's just like having no inverters anywhere in sight. So when the clock goes from 0 to 1, each of these should take its corresponding D input, remember what that value is, and show it on its corresponding Q output. And be careful of the pin numbering, right? This is Q, D, D, Q, Q, D, D, Q. And on the other side, it's Q, D, D, Q, Q, D, D, Q. So it changes every other flip-flop. Which one's on the left, which one's on the right. You gotta keep coming back to the diagram. And then output control has a little inverter here, and output enable does not have an invert, so this is probably gonna have to be tied to a 0, but let's look at the truth table. So 374, if output control is high, then the output has a value that's called Z. Okay, Z is a new output value. We got 1s, we got 0s, we got don't cares, we got previous values. Z is what's called a high impedance output. Electrically, it's like disconnecting the output from anything. It's not a 1, it's not a 0, it's disconnected, it's floating. Okay, it's called a high impedance state. So we don't want that. We want 1s or 0s. So we always want this output control to be pulled low. So down here, pin 1, connect that to ground. Otherwise, nothing happens. All right, and our clock goes in on pin 11, and then pin 1 gets latched, comes out on pin 2, pin 4 gets latched, comes out on pin 5, and so on and so forth. All right, so we got 8 flip-flops. How are we going to use that to make this delay circuit? This is like the best circuit ever. Here's 2 D flip-flops. There's an input and an output. There's an input and an output. Here's our clock. We're going to do the following. So here's in, here's out, and here's our clock. All right, what does the circuit do? What happens the first time that the clock ticks from 0 to 1? What goes on inside this circuit?
D1 becomes
Yeah, so what's this output here going to be?
that's going to be the input of D2.
Right, it's going to be whatever the input is over here, and that's also going to feed the input of this flip-flop. What's going to happen on the next clock tick?
Whatever's in the second D flip-flop is going to output.
Yeah, whatever is on the input here, which was the value that you saw 2 seconds earlier, that's going to appear on the output. Right? And if this input has gone low, that low will come through to here, but you won't see it on the output until another 2 seconds has passed and it gets ticked again.
Does that mean that it takes 2 clock ticks or you go from the input straight to the output?
It takes 1 clock tick to go from here to there and a second clock tick to go from there to there.
Yeah,
So it's going to be 2 to 4 seconds. Right? If you set the input right before the clock ticks, right, basically after a millionth of a second, the clock's going to tick and your input will be here. 2 seconds later, it'll come on the output. If you set the input right after the clock tick, it's going to be a full 2 seconds before it gets to here and another 2 seconds before it gets to there. So this delay between input and output is going to be between 2 and 4 seconds, assuming that your clock is pulsing every 2 seconds. So this is a 2 to 4 second delay. All right, so that's experiment 1. Taking a picture. Yay. Implement a 2 to 4 second delay using those two. So what do you need to write up here, right, for your lab report? You're going to do all of this work. You're going to build this. You should talk about this in your lab report, right? Remember, you're trying to let somebody else reproduce your results. So experiment 1, we implemented a 2 to 4 second delay using this and this, right? Here's a system diagram. Here's a timing diagram for what we expect. Here's a block diagram of the implementation, right? And then show a wiring diagram. So you can put pin numbers on here, right? Which pin were we using for this, which pin were we using for that, and so on and so forth. And if you've got a switch here, you can show a switch. If you got an LED there, you can show an LED, right? And then don't just stop there, right? We tested our circuit. We flipped the switch, and 2 seconds later, the LED came on. And we flipped the switch again, and 2 seconds later, the LED went off. Put in your observations, right? So even though this is a 2-sentence description of the experiment, your write-up should be a lot more than 2 sentences, right? You need to say what you did, how did you design, how did you implement, how did you test it, what did you observe, all that kind of stuff. Okay, because this is the key to making experiment 2 work. So you want to thoroughly document experiment 1. Yeah.
So how do we configure it to make it so that it ticks every 2 seconds?
So your clock is coming from your 555, and that's already ticking every 2 seconds.
Oh,
So you just take the 555 and you put that in.
From the last line.
Yeah, exactly. Right? So that's part of your circuit diagram. You got a 555, you got all the setups, you got the component ID block showing where power and ground are. Take pin 3, run it into pin 11 on this, right? And then, I don't know, maybe take your input, put it on pin 3, take pin 2, connect it to pin 4, take pin 5, run that to your output. Show pin 1 connected to ground, and then mention your ground and power connections in your component block. All right, yellow light. Let's take a break. We'll do yellow light when you come back.